Okay, welcome once again into the class of number theory, and we are doing here the chapter of congruences in number theory. So I'll take some 2 or 3 important theorems in this video, and then in the next video most probably I'll move on to the Chinese remainder theorem, which is very important, which is very useful to solve linear congruence equations and their systems. So in this video we are going to start with this theorem. Write down the statement and then we will move on to the proof. Statement is, if mn are positive integers with GCD of m and n is 1, then phi mn is equal to phi m into phi n. Or in other words, you can say that phi, that means the Euler's function, which is an arithmetic function, is a multiplicative function. So here we are going to prove that the Euler's function is a multiplicative function. So this question may also be asked in your examination in this form. Prove that the Euler's Torsion function is a multiplicative function. So this is the statement here. And once again, I recall what is this Euler's Torsion function. Earlier in the previous video I have told you about this function, but once again I am going to repeat it. For example, if you are having any number m is equal to 10 suppose, then first of all make the reduced residue system, that is 1, 2, 3, 4, 5, 6, 7, 8 and 9. This is the residue system, least positive residue system, leaving 0. And now from these pick up only those which have GCD 1 with the number m, that is 10. So GCD of 1 and 10 is 1, so we will keep 1 here, we will not remove it. GCD of 2 and 10, GCD of 2 and 10 is 2, we know it all very well. So whenever the GCD will not be 1, we will remove the number from here. So this 2 is removed. Now GCD of 3 and 10 is 1, so 3 we will keep here. GCD of 4 and 10 is once again 2, so we will remove 4 from here. GCD of 5 and 10, GCD of 5 and 10 is 5. It is not 1 once again, so we will remove 5 from this set. GCD of 6 and 10, GCD of 6 and 10 is once again 2, it is not 1, so we will remove 6 also from this set. Then GCD of 7 and 10 is 1, so I will keep 7 here. GCD of 8 and 10 is once again 2, so we will remove 8 from here. And GCD of 9 and 10 is 1. So this is the reduced residue system modulo 10. And how many members are there in this reduced residue system? These are 1, 2, 3 and 4, and this is the value of phi 10. So your phi 10 is 4. That means phi of m is the number of those natural numbers which are less than m and which are co-prime to m. So this is your Euler's Torsion function, and now we will move on to the proof of the theorem which we have written earlier on the top here on the board. You can see that if mn are positive integers with GCD of m and n is 1, then we will show that phi mn is equal to phi m phi n, and this property is known as the property of multiplicative functions. So how to prove this? So I am going to prove now. Prove let R is equal to R1, R2, R3 and so on, R phi m you can say, and S is equal to S1, S2, S3 and so on, S phi n be the reduced residue systems modulo m and modulo n respectively. So what is R? It is the reduced residue system modulo m. So how many members should be there is phi m. So I have written the last one as R phi m. Similarly, this S is the reduced residue system modulo n. And how many members should be there? Phi n. So I have taken the last one as S phi n. So these are the reduced residue system modulo m and modulo n respectively. These we have supposed. Now consider this set. Consider T is equal to NR plus MS, where your R is coming from the set R and your S is coming from the set S. So consider this set where your R is coming from the set R and S is coming from the set S. Now look that we will show that this T is a reduced residue system modulo Mn. This we will show. And then how many members are here? How many choices for R you are having? So you are having R1, R2, R3, R phi m. So how many choices are there? Phi m choices are there. And for each choice of R, suppose you have taken R to be R1. For R to be R1, how many choices of S are there? Phi n. So for one R you are having phi n S. So for phi m R's, how many total combinations will be there? These are phi m into phi n. So that means your set T. So this means T has phi m, phi n elements. This is the number of elements of T. Now, if I show that T is a reduced residue system modulo Mn, then you know that reduced residue system modulo M, how many members are there? Phi m. Reduced residue system modulo N, how many members are there? Phi n. Reduced residue system modulo Mn, how many members should be there? Phi mn. So number of members should be phi mn, and we have shown that T has phi n members. So that will mean that phi mn is equal to phi n, because T is actually having phi n members. But since we are going to show that T is reduced residue system modulo Mn, so the number of members should be phi mn. So phi mn must be equal to phi n in that case. But before going to that, we will have to prove that T is a reduced residue system modulo Mn. For that, we will have to show basically three things. Firstly, we will show that this NR plus MS is co-prime to Mn. That means GCD of each member of this set T with Mn is 1. This is the first thing we will show. Secondly, we will show that no two members of the set T are congruent to each other modulo Mn. No two members of the set T are congruent to each other modulo Mn. This is the second thing we will show. And thirdly, we will show that if x is any positive integer with GCD of x and Mn is 1, then x is congruent to exactly one member of the set T. That means there will be some NR plus MS such that x is congruent to NR plus MS modulo Mn. These three things we will show, and by showing these three things, it will be clear that T is a reduced residue system modulo Mn, and that will make your phi Mn is equal to phi n. So what we are going to prove? These three things now. So I am going to rub these, because now I am going to prove the three things that I have just told you what the line of proof we are to follow. So the first of all, we are to show that GCD of NR plus MS and Mn is 1. This is the first part we are to show. Now look that GCD of Mn is given to be 1. GCD of Mn is given to be 1. R1, R2, R phi m. R1, R2, R phi m. These are the members of reduced residue system modulo M. That means the GCD of R with M is also 1. This GCD of M and N is 1. I can also write it as GCD of N and M is 1. I can write, because GCD of 2 and 3 is 1, definitely GCD of 3 and 2 is also 1. Now GCD of N and M is 1, GCD of R and M is 1. So N is co-prime to M, R is co-prime to N. That means N has no common factor with M, R has no common factor with M. So that means their product NR is also having no common factor to M. This means NR and GCD with M is 1. Now note that if GCD of A and B is 1, then if you add any multiple of B to A or any multiple of A to B, GCD will remain 1. That means if you add here K times B, GCD will be still 1. And if you add T times A in B, the GCD will still be 1. So that I'm going to use here. NR and M, GCD is 1. So if I add to NR a multiple of M, that means MS, the GCD will still be 1. So GCD of NR plus MS with M is 1. Once again, I'm writing it as again, once again, M and GCD is 1. And GCD of S and M, S of N, S and N is 1. Because S is a member of reduced residue system modulo N. So GCD of S and N will be 1. Now GCD of Mn is 1, GCD of Sn is 1. That means GCD of Ms and N is 1. Once again, using the fact here, if you add any multiple of N to this, the GCD will still be 1. So you add a multiple NR of N in MS. So GCD of MS plus NR with N is 1. Now look at NR plus MS is here, NR plus MS is here. GCD of NR plus MS with M is 1. GCD of MS plus NR with N is 1. And if GCD of AB is 1, GCD of AC is 1, definitely GCD of A and BC is 1. And that result I'm going to use here. NR plus MS, M, 1. NR plus MS, M is 1. So this means GCD of NR plus MS with the product of these two, Mn, is 1. So that means each member of the set T is co-prime to Mn. This was the first thing we wanted to show. So we have shown that the members of T are co-prime to Mn. The first thing. Secondly, we are going to show that no two members of the set T are congruent to each other modulo Mn. So this I will prove by the way of contradiction. If possible, suppose, if possible, suppose there are two members NR1 plus MS1 and NR2 plus MS2, and they are congruent to each other modulo Mn. Suppose, if possible. So we will arrive at some contradiction, and that means our supposition is wrong, and hence no two members of the set T can be congruent to each other modulo Mn. So from here you can say that your Mn divides this difference, and what this difference is, this is N times R1 minus R2 plus M times S1 minus S2. From congruence to divisibility. Now further, your M divides Mn. m divides mn and mn divides this quantity. So you can directly say that m divides this quantity. So you can say that your m divides this quantity. And m already divides m times s1 minus s2 because it is a multiple of m. Every multiple of m is divisible by m. Now m divides this, so m must divide their difference. And when you will take difference, these two will be cancelled out. And what you are left with, m divides n times r1 minus r2. And what is GCD of m and n? GCD of m and n is 1. We know that if A divides BC and GCD of A and B is 1, then A divides C. And this result I am going to apply here. This is your A, this is your B, this is your C. A divides BC and GCD of A and B is 1, so A must divide C. So this means your M divides R1 minus R2. And this means your R1 is congruent to R2 modulo M, and this is a contradiction. Why? Because R1 and R2 are the members of reduced residue system modulo M. And no two members of reduced residue system modulo M can be congruent to each other. So how this R1 and R2 can be congruent to each other modulo M? So it is not possible. It is a contradiction. And why this contradiction is there? Because our supposition was wrong. And what was our supposition? We have supposed that two members of the set T are congruent to each other modulo Mn. So this is not possible. That means every two members, if you take any two members of the set T, they are not congruent to each other modulo Mn. So two things we have proved. We have shown that the members of the set T are co-prime to Mn. Secondly, we have shown that no two members of the set T are congruent to each other modulo Mn. And finally, we have to show that if x is any positive integer such that x is co-prime to Mn, then x is congruent to some member of the set T modulo Mn, and that will make the set T a reduced residue system modulo Mn, and that will mean T has phi Mn elements, but we already know that T has phi m into phi n elements, so phi Mn will be equal to phi m phi n. So we are moving on to the final step of this theorem. That means if x is any positive integer such that x is co-prime to Mn, then there is a member in the set T which is congruent to x modulo Mn. Let x be any positive integer, you can say z plus. If x is any positive integer such that GCD of x and Mn is 1, then we have to show that you just take A instead of taking x. Let A be any positive integer such that GCD of A and Mn is 1. And this means, since GCD of A and Mn is 1, this means GCD of A and M is 1 and GCD of A and N is also 1. Now, what about the GCD of M and N? It is already given that it is 1. And we know that if two integers are co-prime to each other, then definitely there will be a linear combination of these two which will be equal to 1. So there must exist integers x and y such that mx plus ny is equal to 1, and multiply both sides of this equation by a to have amx plus any is equal to a. Keep it just here and we will use it later when it will be required. So it is an equation we have kept in reserve to be used later on. Now, GCD of A and N is 1. GCD of A and N is 1. GCD of A and N is 1. And note that GCD of x and n is also 1. Now the question is why? GCD of x and n is 1. Why? Because a combination of x and n is equal to 1. If a combination of two integers is equal to 1, then these two are co-prime to each other. Since a combination, linear combination of x and n is coming out to be 1, because m and y are positive integers, therefore x is co-prime to n. So GCD of x and is 1. Similarly, an is 1 we have used, am is 1 now. Am is 1. And from the same equation, you can draw that GCD of m and y is also 1. Because a linear combination of m and y is also equal to 1. Because x and n are now integers. So GCD of an is 1, GCD of xn is 1, GCD of am is 1, GCD of ym is 1. Now look at these two. GCD of an is 1, GCD of this xn is 1. That means the GCD of the product a and x with n is 1, and similarly GCD of ay with m is also equal to 1. GCD of ax n is 1, GCD of ay m is 1. Now ax is co-prime to n, and S was a reduced residue system modulo n. If any integer is co-prime to n, then it must be congruent to some member of the reduced residue system modulo n. So there must be some S. So there exists, you can say S belonging to the set S, such that your ax is congruent to S modulo n. And similarly, ay is co-prime to m. That means in the reduced residue system modulo m, there will be a member R which is congruent to ay modulo m. So, and there exists R in the set R such that ay is congruent to R modulo m. Now look that I'm keeping this equation, I'm rubbing the part written above this line. Now from here n divides ax minus s, and from this m divides ay minus r. Or you can say your ax minus s is n times k1, and your ay minus r is m times k2. Or you can say your as is r plus nk1, and your ay is r plus mk2. Now substitute this value of as, and I want to replace these values ax minus s and ay plus r. Actually I want to use this equation, but I think there is some problem. Amx, axn, ay, ax, I've made a little mistake here. So once again I'm going here. Ax minus s. Actually it is ay minus ax minus s. Sorry, ax minus s is nk1, and ay minus r is mk2. Okay. Now it is okay. So here you are having ax is equal to this and ay is equal to this. Now we are on the right track. Now this ax I am going to substitute here, and this ay I am going to substitute it here. So what you will get, m r plus nk1, the value of ax, plus this n and value of ay, r plus mk2 is equal to a. So now just simple calculation, simple terms. So what you are going to get here, mr, this one, and once again I have made some mistake. This is s, so this is not r, this is s. So this is ms and this is nr. This is nr, and what else you are going to get here? mn k1, mn k2. So mn k1 plus k2 is equal to a. So take this ms plus nr from the left hand side to the right hand side. ms plus nr. So that means mn divides this term. So this means mn divides a minus ms plus nr. So this means a is congruent to ms plus nr modulo mn. And that what we wanted to show, that if a is any integer co-prime to mn, then there will be a member of the set T which is congruent to a modulo mn. And now by proving these three things, number one, every member of the set T is co-prime to mn. Secondly, no two members of the set T are congruent to each other modulo mn. And thirdly, if any integer a is co-prime to mn, then there is a member in the set T which is congruent to a modulo mn. It makes the set T a reduced residue system modulo mn. And that means number of members of the set T is phi mn. But what is the number of members of the set T? We have already checked. It is equal to phi m, phi n. So phi mn is equal to phi m, phi n. So here I am going to stop this video. In the next video we will try to prove Euler's theorem, Fermat's relative theorem, and many other theorems and results. Till then, thank you once again.